everyone. My name is Rongxian Wang. I'm here to present our work, WhisperFlow, speech foundation models in real time. So here's a short summary. We're targeting to reduce the latency of streaming speech processing with speech foundation models. And to reach this goal, we contribute 3 new techniques. Hashword to reduce the encoding cost of speech foundation models, and beam pooling to reduce the redundancy in streaming speech processing decoding, and CPU-GPU pipelining to improve the hardware utilization. And with all these 3 techniques together, we build our system, WhisperFlow, which is a runtime system that serves the speech foundation models on the streaming speech processing task. And with our system, we achieve 2 times latency reduction compared to the baseline Whisper streaming system, and it can run fully local on the laptop I'm currently using. And we also have a demo that I will show you later. So let's first look into the demo. And let me first run it. So here's the demo, and so yeah. So here's a live demo. On the top, we show the audio waveform, and we can see that the streaming audio keeps coming in. And we run the Whisper medium model for this task with our WhisperFlow serving system. We can see that the transcript is showing in real time, and it's also timely aligned with the audio waveform shown above. The latency is also pretty low. It's actually less than 1 second. And let's also look into the baseline system. So we want to let it run for a while and check the processing interval as well as the latency after we get a longer audio context. We can kind of perceive that the difference. And generally, the baseline system have a longer processing interval and also a longer per latency. It looks like it's still quite capable, but that is because my laptop is quite good. If you move to like a weaker device, then the difference will be more significant. Okay, that's the demo, and I will also show this in the demo session, so you're more than welcome to check it further. And yeah, let's return back to the talk. And yeah, the task we're targeting to solve is the automatic speech recognition, which transfers the speech to the transcript. And there's a long history on this task, but the current latest method we have is speech foundation model. More specifically, we are targeting to solve the streaming speech processing task, which, as we have shown in the demo, we have the streaming audio as the input, and we want to show the streaming transcript as the output. And the key metrics in the task is per word latency as well as the transcript accuracy. So the model involved in our product is the speech foundation model. We take the OpenAI Whisper series as an example, as shown on the slide. It is a transformer-based encoder-decoder model, and there's a series of model, and the size scales from 30 million parameters to 1.5 billion parameters. It's trained with a large volume data. It's 680,000 hours of audio with 97 different languages. And thanks to this large chunk of data, the model has outstanding generalizability. It can perform very well on unseen data, and people have built various applications on top of it. And during the model processing, the model usually processes a fixed length input. So basically, the audio for Whisper, the audio will be paired or trimmed into 30 seconds before the model processing, and then the audio will go through one-pass encoding with the encoder, and then token-by-token decoding with bin search algorithm with the model decoder. And let's take a closer look to the bin search decoding. So we will always start from the start of sentence token, and in each decoding round, we will develop the next round tokens, and with multiple hypotheses in parallel to form a bin in the bin search. And we do this in multiple rounds to develop the next token, and one by one until the end, and we'll pick the hypothesis with the top probability as the final result. And there are a few different schemes for the current system to perform this streaming speech processing with the foundation models. So first of all, we have the batch processing, which is the default approach for the Whisper model to process the audio. So we will wait for every 30 seconds to get the 30-second audio chunk and let the model to do the inference and get the transcript. The good thing is that basically that's the default approach, so the model will provide a transcript with the goal accuracy. But the problem is that if we wait for every 30 seconds, then for the earlier part of the audio, the latency is just too long. And basically this does not fit the streaming scenario. And the latest system we have, the state-of-the-art system, is the Whisper streaming system. So in this system, the system adopts a sliding window audio buffer on top of the streaming audio. And it's around 15 seconds, and it will keep moving forward. And in every processing round, we will have Whisper model transcript do this transcription on top of this sliding window audio buffer. And after we get the transcript, we'll check the transcript and see if there is a token that's shown in the consecutive round of processing result. Then we'll confirm it as the final result. And with the sliding window audio buffer, the Whisper can perform the inference much more frequently compared to the default approach. And as a result, the provoked latency is much shorter. But the problem is that with much shorter processing interval, the computation is also increased largely. And for the mobile device and client-side device, the computation is just too much, and it cannot handle it efficiently. And so to move such a system to the client-side devices, we located a few inefficiencies in the system processing. First of all, there are inefficiency in encoding. So as we mentioned, the speech foundation model usually take a fixed length input. For Whisper, it's 30 seconds, and in our system, the audio buffer is around 15 seconds, so there's like tens of seconds of padding, and this padding introduces redundant computations. But at the same time, removing this padding is a non-trivial problem. As shown in the table on the right side, we can see that if we simply remove padding or cut the padding shorter, then there will be severe hallucinations in the output, and as a result, the overall accuracy will also drop significantly. So we need some like non-trivial approach to remove or replace the padding. And also, there are inefficiencies in decoding process. As we mentioned, the common approach for speech processing decoding is a bin search decoding, and we will develop a few hypotheses in parallel, and this introduce more computation. And in the streaming speech processing with sliding window audio buffer, in consecutive rounds, there are large overlap in the input audio. And as a result, there will also be a large overlap on the transcription result. As shown in the figure below, we can see that compared to the first round result, the second round decoding, the earlier tokens are just the same. And as a result, the red part computation is actually redundant. And also, there are inefficiencies in hardware utilization. So the Whisper streaming system, the sliding window audio buffer approach, is originally designed for the server-side GPU, so it's run on GPU only, and assume the GPU is quite capable, and largely leave the CPU idle. But on the client side, the hardware is quite different from the cloud side. We find that the CPU is actually quite capable on some of the workloads. So for example, as shown in the table below, we test the Whisper medium model on M2 Pro chip MacBook Pro, and we find that although for decoding, the GPU latency is much shorter than CPU, but for decoding with different bin size, we find that GPU latency is actually comparable with CPU latency. So from this result, we feel like if we can somehow use the CPU in the processing as well, then the latency can be further reduced. But it's also a non-trivial problem, and I will introduce our techniques later. So targeting to solve these inefficiencies, we propose our three designs. The first design is Hushword, which is a learned audio segment to replace the long padding. As shown in the figure here, instead of pad longer than 10 seconds zero after the original audio buffer, we replace it with a 0.2 Hushword audio segment trained by ourselves. And basically the model will as expected, the model will output the same transcript compared to the default padding. And to get this hash word, we need to train it from scratch. So during the training, we follow the adversarial attack scheme. So we will first initialize the hash word as a random vector and attach it at the end of the training data. And the model is also involved in the training, but the parameter is frozen. So only trained parameter is the hash word itself. And the label we use is just the original transcript as we used in the original model training. And we find that after a few rounds of training on a small data set, the hash word can be trained to be converged to a certain point, and it can actually replace the default padding and perform the correct inference with the input audio. And second design, beam pruning, targeted to solve the decoding inefficiency problem. So it is actually a reference-based bin size reduction method with a fallback mechanism. So we will take the first round transcription result as the reference, and when the new decoding starts, for the first token, we will first do a reference aligning, because the consecutive round sliding window audio buffer is not necessarily aligned. So we need to first align them together. And so we'll just simply do a linear search to find the first match token. And then we'll continue to do the decoding token by token and try to match the token with the reference, the current decoding token with the reference token. If there's a match, then we will just keep the bin size to be 1, which is same as greedy decoding, and it will save a lot of computation. And during the matching, we also skip some of the tokens, like punctuation tokens, timestamp tokens, and some other special tokens, because the Whisper model is not that consistent on such tokens. And until there is a mismatch between the reference and the current decoding session, we will let the current decoding session fall back to the original bin size to preserve the decoding accuracy. So as a result, we will save the computation marketing green part here. And to solve the hardware utilization problem, we have our CPU-GPU pipelining design. To wisely use the hardware resources, the first thing we need to do is to characterize the workload involved in the system. So the first thing we do is to profile the original Whisper streaming system on top of the client-side devices we have on both CPU and GPU, and compare the latency. And we find that only decoding can work efficiently on both CPU and GPU. So as a result, we propose our GPU prioritized pipelining design. So we will try to opportunistically offload the decoding session to CPU whenever it's idle, but keep all other workloads on GPU. And here's a visualization of our pipelining design. But I won't go into that detail about this design, because there's a lot of details. And if you're interested in this, you can check the paper or talk to me offline. And with all three designs, we build our system, and it consists of two parts: the offline part and the online part. In the offline part, we will train the hash word for each of the model variants, and also we will do some hardware resources profiling with some test data to decide some hyperparameters for the model, for the system. And in the online part, we will have all three techniques applied and deliver the best latency during the processing. And here's some evaluation methodology. We test our system on a PC with different Apple silicons, as well as Orange Pi 5. And we test it on popular data sets, measure the accuracy, as well as the per token latency. The model we choose is Whisper medium, small, and base with different parameter size. And we choose Whisper streaming as the baseline system. And we also test two of our variants. One is without CPU-GPU pipelining, another is with CPU-GPU pipelining. And here's the end-to-end result. We can see that on 3 different model variants on 3 different hardware platforms, our system can consistently provide more than 2 times latency reductions compared to the baseline Whisper streaming system. And here's a closer look of the latency and accuracy trade-off. We can see that compared to the baseline system, our system can run with a shorter processing interval, and as a result, it delivers a shorter per word latency. But at the same time, the accuracy actually does not drop that much, and which means that our system can effectively preserve the processing accuracy. And here's an application study. We add all 3 techniques on top of the Whisper streaming system gradually, and we find that all 3 techniques contribute to the latency reduction, actually. And here's the last evaluation only about the hash word. We test the hash word on 4 different data sets and test the encoding cost shown on the x-axis and the accuracy shown on the y-axis with different padding reduction strategy. And we find that compared to other strategy, our method can hit a sweet spot that delivers the lower computation as well as higher accuracy. Okay, here is a summary. In this presentation, I introduced the WhisperFlow, our streaming speech processing engine that serves the speech foundation model in this task. And we introduced 3 different techniques: hash word for encoding redundancy reduction, and bin pruning to solve the decoding redundancy, and CPU GPU pipelining to improve the hardware utilization. And with our system, we can reduce the per word latency in the task by 2 times. And the system can run fully local, and we also have a demo. Thank you.
All right, let's thank the speaker. While the questions are getting ready, I have one question. Can this be applied to other tasks apart from converting speech to text, maybe like translating the text from one to another language, sometimes at international conferences?
Yeah, that's a good question, actually. The speech foundation model is quite capable. It's not only capable on transcription, it's also capable on translation, actually. So, and we actually tried, but didn't evaluate it throughout but we find that our system can also adapt to the translation task, but it does not work as well because the translation is a non-linear process. So at some time, the earlier part, the later part will change the earlier part quite largely, so the system does not work as well, but it can work.
Yeah, no, especially languages like German, where the end context changes the whole sentence.
Yeah.
Anyway, questions?
Okay, very impressive work, and this is Le Min from Hong Kong PolyU. And my question is that, so speaking of speech foundation model, it reminds me that the ChatGPT app supports audio input and audio output. So I'm curious that can your system extend to these kind of models?
As the OpenAI is actually closed AI, so we don't know what happened behind the scene. But I guess I would assume that our hash word approach will still be worked on the encoding part of their model, because I would assume their model will still have an audio encoder. I don't know what kind of decoding strategy they use, but if they use bin search, then our bin pruning will work. If they don't use bin search, then maybe we can still apply some kind of speculative decoding to just share the same spirit with our method to improve the decoding efficiency of their model. And for the CPU GPU pipelining, as they use servers, so I guess they don't need this.
Yeah, sure. Okay, thank you very much.
All right, if there are no more questions, we'll end the session here. We finished 10 minutes early, so you have a